accessed newly in the kth round. So observe, the number of accesses to the database is not dependent anymore on the number of records in the database, only dependent on the number of previously asked queries.
Yeah, but I have a question. Since I would expect a lot of users making queries,
Right.
very soon we will end up having for a query to access the entire data set.
Yeah, that's right. So now that's a valid question, and that's what I'm trying to answer with these two lines. I'm asking myself, when is the amount of work too big, and when should I start to reshuffle? And that's an optimization problem. And by simply taking some kind of very simple example, very simple computation, you can say, after you ask square root of n queries, then you have to re-encrypt and reshuffle. Yeah? Which still might be a big number, because the number of queries is now dependent on the size of your database. Yeah? But think of about 1 million tuples. The square root is 1,000. Yeah? So it's still a big number. And that's exactly what also motivated us to look for different solutions. Okay? Let me dwell with one more sentence on this solution. If you really look very carefully, we really haven't changed that much on the n-squared algorithm. We only have shifted the work a little bit around. The shuffling and encryption is done in n times square root of n, and the access is now independent. But if you put both together after square root of n queries, you reshuffle. So on a per query basis, you still have a complexity of O to the n. So it's still not very good. Yeah? So the question is, what can you do about it? The next step, we said, well, if it is so expensive to maintain perfect privacy, maybe the user is willing to give up a little bit of his privacy, and I explain in a minute what that means, and therefore gets better, meaning algorithms that run faster, having a lower complexity. So you would really like to have a way that the user can decide which way he or she wants to go. More privacy means more work. Less privacy means less work. So we initially came up with a very simple, algorithm. And let me give you, first of all, the basic solution, which is not the ideal one, a basic solution. And it helps you to understand then the next step. We maintain 2 copies of the database. One copy, I show here, on the left side of the secure coprocessor, is the reshuffled and encrypted database. And on the other side, we have the original database where all the records are unencrypted and stored as initially done in the database. So when a query comes in, and we assume here also that we know that it's the kth query, we access the kth record in the encrypted and reshuffled database. Notice that this leads to an access in the encrypted and reshuffled database that is sequential. And if that record is the requested one, we randomly take one access to the original database. If it is not the requested record, in order to answer that query, we have to access the requested record from the unencrypted database. So the adversary knows one of the 2 accesses, let it be to the encrypted one or to the original database, must be the answer to my query. So what is the likelihood, the probability that I catch the one from the encrypted database? It's 1 over n. Okay? So the likelihood that it is not that one is 1 minus 1 over n, and that's the likelihood that the record that I retrieve from the original database is the request or the record requested by the user. I don't have to tell you, depending on n, it gives you a big likelihood that the answer coming from the original database is much more likely than coming from the encrypted database. Okay? But again, realize that I'm shifting now the probability of one record being very likely to be the answer from the rest. And so I have an unequal probability for every record in the database. And that's what I call with the term probabilistic privacy. It's not the likelihood for every record to be in the answer is not the same anymore. There's a difference. Okay? So if you look at this algorithm, everyone would say, bad one, bad one. So slight change will help to remedy this problem. So what we do is we introduce two knobs, I would say. I call them A and B. A determines how many tuples do I access sequentially on the encrypted database, and how many random records, or how many records do I access randomly on the original database. So I can now play with these two knobs. And they have a very important impact on the probabilities that I now have. Let me now, before I get to the probability distribution again, let me give you the algorithm again. So what I do is, for the kth query, I access sequential access again on the encrypted database, the records starting with k times a up to k times a plus a minus 1. Okay? One of them might be the requested record. The adversary cannot distinguish. I know if it is one of them, then I can freely choose the B random records accessed from the original database. If the requested record is not among the A records, then I have to go to the original database, have the choice of B minus 1 being randomly selected, and 1 must be then the record that is requested. So notice that the probability on the encrypted database really doesn't change. But the probability on the original database is now influenced by these two knobs, A and B. It increases somehow the quotient that is deducted from 1, and then it's divided by B. So what the effect is that this difference between these values really gets less and less. In some sense, the bigger A and B are, the more equal these different, or the probability for the different records in the database system will get, or the smaller they are, you widen the gap. So you now have a way to somehow influence how much somehow the probabilities for some records might be different from the ones that are less likely to appear. So I don't have recorded now the exact numbers for A and B here, but you get this kind of picture. So you have here 3 records that are quite likely to appear, and the others are much less likely to appear. It's actually, 1 over n times 1 over n minus 1 if you figure it correctly out, with A and B also somewhere in there. So this is more or less, and what changes is more or less the gap between this probability and this probability by making A and B larger, or then the gap gets less, or making them smaller, then the gap widens. So I give now the user, even though he or she might not understand what the probability values are there, a way to turn these knobs. A and B determine the number of accesses to the database. More accesses, better protection, better privacy. Less values, less privacy. Okay? But again, if you look careful, it's probably not very satisfying, because you can ask, what are the values for A and B? The user might not really have a good sense. He might only recognize that with some A and B values, the amount of work, the number of accesses to the database goes up. What does he or she get for it? I mean, if you give back privacy is 0.7, I really don't know. So let me come to the last solution that I present to you. And here I also want to go in 2 steps. I give you first of all the naive solution, which has some deficiencies, and then I'll upgrade this one with some kind of interesting